Welcome to Controversy 2. Why do our bodies grow old? Let's go over a few basic definitions before we get into some of the theory behind this question. First of all, the maximum lifespan for human beings is about 120 years old. So maximum lifespan is the maximum number of years a certain species can live. We have no valid records of people living much beyond 120 years. Life expectancy, on the other hand, is different from lifespan because life expectancy defines the average number of years a person will live, and that has risen. Life expectancy has a lot of different factors that can be influencing how long a person is expected to live. The year they were born, whether the person's male or female, what cultural background they have. So again, over recent years, life expectancy has risen, but lifespan hasn't really changed much at all. And this difference between life expectancy and lifespan is really important to understand because of the next theory, which is compression of morbidity theory. So this theory is, first of all, the whole goal really here is to help a species, this is for more of a species level thing, to make the space between a person's life expectancy, so the average number of years he or she is expected to live, and their lifespan, the maximum number of years a human being can live, to make the space between those things as short as possible. To make the space between morbidity or illness and mortality, death, to make that space as small as possible. So we really are aiming for a healthy old age followed by a rapid decline and death. So if we had that, a shorter time to be sick before we die, the argument here is that it would enhance a person's quality of life. It would extend life expectancy and health span or healthy span. And as a result, it would reduce the healthcare costs and caregiver burden of having to take care of someone who's ill for a very, very long time. And I'll use an example from my own family. My father's parents died within a year of each other. My grandmother, she died at age 87 after having had Alzheimer's for about 6 years. So 6 years before she died, she became ill enough to need a lot of care. Her quality of life arguably declined, and it took a long 6 years of declining health for her to then reach the end of her life. Compare that with my grandfather, who at age 90, now granted, he had some chronic health conditions. However, he was fairly independent, living on his own, able to take care of himself until the day he died in his garden doing what he loved at age 90. So I would argue to say that his end of life was probably a better quality than my grandmother's end of life. And so again, really the goal is to compress that period of time between sickness and death. Okay, so let's talk a little bit more about the nitty-gritty of how our bodies age. First thing is to understand, and we will talk about senescence again in a little bit more detail, but our normal aging process is this process of senescence. It's an underlying time-dependent biological process. Itself is not a disease. However, this natural aging process does involve functional loss and increased susceptibility to disease and death. So Gompertz is a researcher who talked about how as we get older, our chances of dying increase. In fact, for humans, every time we make it another 8 years, we are twice as likely to die than 8 years prior. So a 38-year-old would be twice as likely to die as a 30-year-old. So every 8 years you pass, you become doubly more likely of dying. Kind of a frightening thought, I would say. Another thing that you should know about this is that at any given age, men are twice as likely to die as women. So keep that in the back of your mind, and we'll talk about it again in a couple of slides. But before we do that, Let's talk about another couple of concepts that will help provide some context and background to the biological theories of aging that we'll explore in just a moment. One of the things that you ought to know is that we often study the structure of different species to help us understand differences in aging and lifespan across species. So we'll look at humans and we'll compare them even to things like fruit flies or mice or primates. So this is called comparative anatomy, and it works because for many species, there's enough commonalities between our species so that the research that we do can apply to both species. This will come up again as we talk about some of the biological theories. So just to give you a quick example, the doubling time for humans is 8 years. So that's that figure that I just mentioned to you, that after 8 more years of living, we become now double or twice as likely to die. For a fruit fly, that happens after only 10 days. And for a mouse, that happens only after 3 months. This is important because we often use mice and fruit flies to study aging processes, because if we waited every 8 years, or if we waited lifetimes of humans to study these things, we'd never get anywhere with science. So we study species that have shorter lifespans and quicker doubling time because we can study processes of aging a lot more efficiently that way. Another concept that's important to understand as part of this puzzle is the rate of living concept. And this talks about the fact that life expectancy is closely related to another process called metabolism. Smaller organisms that have faster metabolisms also have shorter life expectancies. So you could also say here that larger organisms that have slower metabolisms have longer life expectancies. So that's important when we start talking about possible environmental things that we can do to slow down our aging. What might be connected with metabolism? And you might also already be thinking of a few ideas. Another thing to realize is that human beings' average lifespan and maximum life expectancy are about twice as great of those of any other primate. So these are all things that we can do to help us understand how humans might be similar to or different than other species that we study. So now let's talk about aging theories or possible answers to this week's controversy: why do our bodies grow old? So it's important to recognize that as we go through these theories of aging, that some theories are actually hypotheses that are no longer valid. So a hypothesis, therefore, gives us frameworks for experiments. It gets us one step closer to understanding what's happening. But theories are kind of our best guess at the moment, but they are disprovable. And some of the theories that we'll cover, they have been disproven or are not regarded as really as possibilities for what's going on. The other thing is that no single theory of aging could possibly explain all of the complex processes that occur in the cells and in the body systems. So keep that in mind as we go through. Why are there so many theories? Which one is correct? In actuality, there are probably more than one that correctly, as far as we know at this point, explain what's happening in the aging of our bodies. There are two basic kinds of theory. One is that aging happens by chance, or the way we age happens by chance, that it's really the result of external events. Other theories prescribe more to this thought of fate, that aging happens as part of an internal necessity. So the question really remains whether or not it's possible to intervene to correct the damage that's done to the aging body, or to modify the genetic programming of our bodies. And that's regardless of which of these two basic kinds of theory is correct, chance or fate. So let's dive into some of these theories. So wear and tear theory was kind of an early theory of biological aging. It sees aging as the result of chance, and it is possibly a good explanation for some aspects of aging, such as the fact that our joints and our bones become damaged over time as an outcome of just living a certain amount of time. Wear and tear theory is not generally accepted as an explanation for how we age in general. Another theory is the somatic mutation theory. And this theory notes that cells can be damaged by radiation specifically. And as a result of the radiation damage, there might be mutations or genetic changes in our cells. This somatic mutation theory is a more modern and sophisticated version of the wear and tear theory, but again, there's little scientific evidence to support it at this point. So kind of building upon those wear and tear types of theories, next we have error accumulation theory, which is also called error catastrophe theory. And these theories say that decremental changes of senescence are the result of chance or random changes that downgrade the genetic code. So in other words, this theory is saying that over time, as we live longer and longer, there are small little errors in genetic coding that happen, and eventually these changes make the later copies of our genes unreadable. So imagine if, for example, you have a piece of paper and you photocopy it and make a few copies, and when you use those up, you take one of those copies and you make another copy, blah, blah, blah. You probably don't make photocopies of photocopies anymore these days because we can scan things or we can find electronic copies. But back in the day, when you would photocopy photocopies, the end result would start to get kind of fuzzy. You maybe couldn't read some of the words. And that's kind of a similar process of what is happening here with error accumulation theory. Accumulative waste theory theorizes that the accumulation of waste products within our bodies and within our cells eventually will interfere with cell metabolism and leads to death. So according to scientific research, although we do accumulate waste products in their bodies, there is little evidence of harm to the organism as a result of this waste products. So again, maybe some valid parts of these theories, but overall not necessarily accepted as the be-all, end-all theory of biological aging. Moving along a little bit here, autoimmune theory says that the system, meaning our organ systems, may eventually become defective and no longer distinguish the body's own tissues from the foreign tissues that it's supposed to be attacking. So as a result, the body starts to attack itself. As suggested, as we get older, there's an increased risk of autoimmune diseases. Not that all autoimmune diseases happen to only older adults. Certainly lupus, which is an autoimmune disease, can happen in younger people, as can rheumatoid arthritis. But as we age, we tend to have a bigger risk of getting some of these autoimmune diseases. Another interesting one is the aging clock theory, and this theory claims that aging is programmed into our bodies like a clock, ticking away, starting from the time that we are conceived. Some used to think that perhaps we had a set number of heartbeats, and when we used up those number of heartbeats, goodbye. This may be a good excuse for not doing anything that might raise your heartbeat, like jogging or seeing a scary movie, but for the most part, this isn't really a widely accepted theory of biological aging. So the next is the cross-linkage theory, and many of you have probably heard of what collagen is all about. We have collagen in our skin and our faces. When we start getting wrinkles, it's usually because there's a breakdown in collagen in our skin. But what you might not realize is we have collagen even in the deeper layers of our bodies, the parts that we can't see. And so this cross-linkage theory claims that the bodily changes we see as we age, and the ones we don't see, result from the accumulation of cross-linking compounds in the collagen. And so those cross-linking compounds makes the skin and organs and the connecting tissue between the organs become stiff. And so that is cross-linkage theory. Free radical theory is yet another theory of biological aging, and specifically it says that free radicals will damage atoms, especially it'll cause atoms to have an extra electron, for those of you who are biologically minded and understand what that means. But the damage created by free radicals, which are molecules that appear as a byproduct of the metabolism of oxygen in our cells, which is necessary for life, Eventually, that damage will give rise to symptoms that we recognize as aging. Because, again, this damage, the extra electron, makes the atom unstable, which can damage parts of our cells. So the body produces antioxidants, which are substances that protect us against free radicals and can prevent damage to our cells. But at some point as we age, we are not producing as many antioxidants, the damage becomes too great, and so we have some of the symptoms that we associate with aging. And that's why we are always told, eat foods really rich in antioxidants to boost that body's ability to take care of the damage caused by free radicals. And you can see here on this slide that here are some of the causes of these free radicals. Things like UV light and air pollution and metabolism and smoking and inflammation. Let's move on to cellular theory. Many cells in our body require cell division to do their job. So again, this one, free radical theory, these are results of processes that have to happen in our bodies so that we can live. But there's damage that also happens when our bodies are going through their natural processes. So as mentioned in relation to the error accumulation theory that we just discussed a few slides ago, cells that are senescent stay in our bodies. They don't just go away and die and we don't get rid of them, but the bodies that are senescent will stay in our bodies and can interfere with other processes in our bodies. Let me back up just a moment, explain what I'm talking about. Cellular theory argues that aging ultimately is the result from the progressive weakening of our capacity for cell division, maybe because we exhaust our genetic material. So there was a researcher, Leonard Hayflick. He wanted to create a vaccine. And so he was growing a virus, the virus for which he wanted to create this vaccine. He was growing a virus inside, he was using fetal lung cells to grow the virus. And he noticed that after a certain amount of time, the cells would just stop growing. Not because he introduced some other thing, it's just they would naturally stop growing. Later, researchers found out that it wasn't that cells would stop dividing or stop growing after a certain amount of time, but there's a certain number of times a cell will divide before it then goes through senescence. In humans, they think that's about 50 times. So all of the cells in our bodies that do divide, and they need to divide for healthy functioning, get to this point of 50 divisions, and then they'll stop dividing. But like I just mentioned, they won't just stop dividing and then go away. The senescent cells, or the ones that stop dividing, will kind of hang out in our bodies. Sometimes that's no big deal, but sometimes these senescent cells hang around and start to interfere with the healthy processes in our bodies. And those processes that they interfere with then will cause what we see as aging. So, is aging inevitable? Well, the biological aging process may not be the result of a rigid genetic program. It might not be that we're programmed to biologically age. However, aging is not a disease. Despite how some people treat aging, aging in itself is not a disease. Aging might make us more at risk for some diseases, but itself, it's not a disease. It's a very natural process and inevitable at this point. So this brings us to the question, okay, if aging is not inevitable, are there things that we can do to at least slow it down? And there are a couple of things that have been discussed as possibilities for slowing down aging or maybe even expanding lifespan, certainly expanding life expectancy. However, there is only one environmental intervention that has scientifically been shown to be connected to longevity in mammals, and that's restricting food intake. So when caloric intake is reduced, and we're talking up to 40% fewer calories than normal, 40%, we're seeing that age-related deterioration slows down. Remember we talked a few slides ago about this connection between aging and metabolism? This is where it probably comes into play, is that caloric restriction slows metabolism. And metabolism is the rate at which food is transformed into energy. So when we reduce calories, slow metabolism, age-related diseases tend to also be diminished. Very interesting. But how many of you would be willing to cut your caloric intake by 40%? That's a question. So for any individual, length of life will be the result of both genetic and environmental factors. Actually, they say that nearly 20 to 25% of how we age is genetic, and the rest has to do with our lifestyle or environmental choices. So that puts a lot more of the responsibility of how we age into our hands. So to kind of sum up some of this is talking back again with this compression or prolongation of morbidity. So these are two separate things. The goal really should be compressing morbidity, meaning having a shorter amount of time that we're sick before we die, instead of prolonging morbidity, which at this point, scientifically speaking, we've found ways to keep people alive longer. But people are now living longer with a longer and longer period of time of chronic illness, sometimes pretty severe chronic illness. So is that really our goal here? Environmental and genetic alterations have been shown to increase lifespan among simple organisms, but although we can do lots of learning by doing experiments on mice or fruit flies, human beings are way more complex, and there's still no conclusive evidence from research on humans exactly how we can go about slowing down our aging. According to the textbook, the compression of morbidity theory stands out as an important reminder of how critical biological research will be for the future of an aging society.